We'll spend the first 10-15 minutes finishing off what was notionally going to be the first lecture. Fortunately, the second lecture will be a bit shorter, so I hope that we will catch up by the end of today. That's slightly early, in fact. One of the reasons I called it shorter is just to have a little bit of a straw poll. So there's a difference between the handout from today and the handout from last time. Last time there were gaps for you to fill in, and I know that one or two of you struggled to get all the gaps filled in. This time I haven't bothered, it's just all there. So hands up who would rather not have the gaps to fill in, and hands up who likes the idea of having something active to do by filling in gaps. Ooh, that's pretty much. I'll try that again. Hands up for if you want gaps, and then if you don't want gaps. That's pretty close, isn't it? I think wanting gaps wins though. Would you say so? No, I think most people. I think we have to go. We can't please everybody. I've learned that long ago. We can't please everybody all the time. But it looks like the majority prefer the gaps. So I'll go back to giving you gaps for the next one.
Take the steak. Stick with it.
Okay. Finally, for anyone someone who either missed the first lecture and doesn't have a copy of the first lecture handout, there's a few spares here at the front.
They'd rather sit scrunched up over there than those seats there.
Okay, now, if we set up on time, I'll also finish on time. So, just to take you back to the end of the last lecture, I had to rush it a little bit towards the end when the structure started getting a little bit more complicated, which is unfortunate. So I thought we'd just go over again, if we're all happy with basic face centre cubic. In that case, face centre cubic, green ones with silver ones in the octahedral holes, 1 to 1. 4 green ones, 4 silver ones in the whole cell, per cell. However, if you've got a 1 to 1 compound, that's certainly one way to do it. If you've got a 2 to 1 compound, you can stick an atom in all the tetrahedral holes. And in this case, it's fairly easy to see that the silver ions, the yellow ions are coordinated tetrahedrally, 4 nearest neighbours. It's perhaps a bit harder for some people to perceive that the cations, that's the red ones in this case, the calciums, have got cubic coordination, 8 coordination, because you can only see 1/2 of cation. If it's in the face, if it's in the face side there, that's only half the cation. So you have to imagine the next cell sat on top of that. And some people are struggling with that, which is why I've prepared this representation of the cell. So again, here is one cell. Those are the 4 corners of the cell. 1, 2, 3, 4. Face centre cubic. And if we're looking at filling all the tetrahedral holes, what I've done is I've filled the tetrahedral holes with little bits of foam which are simulating the fluoride ions. So if I turn it on its top, that's us halfway through a face-centered cell, and start dismantling it, we can see, hopefully, that we've got 4 at the top there, and those 4 tetrahedral holes. Take all that off, and then I've got 4 at the bottom in those 4 tetrahedral holes. So there was a cubic lattice of foam bits. 2 there, 2 there. Slice that in half, another 2 there, and another 2 there. So that's what we've done, is slice the cell right away through the middle of that calcium atom there. And so that is 8 coordinate, and it is cubic. Whereas it's fairly easy to see the anion combination in this case. So you do have to develop that capacity to imagine the next cell and perceive the geometry. So that's a very common case if you've got a 2-to-1 ratio to deal with. If you've got 2-to-1 the other way, where it's two metals and 1 anion, then it's called acid fluoride. Back to another case for zinc blend, so another 1-to-1 case, because that's zinc 2 plus sulfides 2 minus, still 1-to-1. You fill half the tetrahedral holes, and that's another 1-to-1 geometry, because there is twice as many tetrahedral holes. There are 8 tetrahedral holes, 1 at each corner, and 4 point atoms. So that's just a bit of what we did last time. There's a picture of the tetrahedral environment and how those tetrahedra are linked through their corners. So zinc blend, you've got tetrahedral for both the cation and the anion, and that's what makes it the same structure as diamond. If you have both the sulfur and the zinc replaced by carbon atoms, then that describes the diamond structure quite perfectly. So counting the atoms in the cell, face size count, how much the face size count? Aha, because you're just sharing one face with another. So we've got 1 in the face there, and how many faces are there on a cube? 6, just like a dice. 6 halves is 3. And then you've got corner sites, and there's 1 in each corner, and there are 8 corners in a cube, so it's 8 times an 8, which is 1. 3 plus 1 is 4. So it's 4 sulfides, and it's easy to count the blue ones, they're all entirely inside the cell, so 1, 2, 3, 4. So that is the cell formula, and that is the empirical formula. And the way that they're linked is by corner sharing tetrahedra, which is how it describes diamond as well. Okay, so that concludes what we call the eutactic structures, those structures that are explainable in terms of simple filling holes in regularly packed lattices. But there are others, of course. Quite apart from before you get all the way to molecular, you can have 2-dimensional structures and you can have 1-dimensional structures, which are also polymeric, so periodic structures. You have to think about those. Another way of thinking about them that we just introduced a little bit by looking at these sorts of diagrams, another way of thinking about structures is thinking about how the coordination polyhedra link together. Sometimes if you've got lower dimensionality than 3 dimensions, this is a better way of thinking about them. So you can have structures which are built by polyhedra, and the cations on the anion neighbours, and you can link them together by corners, as you saw there, or along edges, or sometimes even along faces. So some examples are there. There's an example where you've got 2 octahedra which are linked by corners, and that could give you a 1-dimensional polymer, or you could extend it out into 2 as well. You can have 2 octahedra linked by edges, or you could even have 2 octahedra linked by faces. And all of those things, you can find examples like that. The classic example for this just edge sharing is rhenium trioxide, a rather inefficiently packed structure, definitely not closest packing, and that tells you that you've got a lot of covalency. And you'd expect a lot of covalency because you've got rhenium 6 plus formally, oxygen 2 minus each, the oxygens is 6 minus, so formally that's rhenium 6 plus rhenium in the oxidation state of 6. And that simple fact that you've got such a big number tells you that you've got significant covalency. You cannot have predominantly ionic bonding when you have a massively huge positive charge, because if you surround that massive positive charge with lots of ions, lots of anions, it will suck some of the electron density back. It will be incredibly polarizing. So by implication, you get some sharing of electron density. So high oxidation states imply covalency, and that gives you this structure where it's just linear oxygen all linked up in a big square lattice like that. Edge bridging, you can have examples from, better write these out I think, yeah, because you've probably got space to add to yours, yeah. Zirconium, which is below, you've got titanium, then you've got zirconium, actually I think it's hafnium, then zirconium. Unfortunately we're in the physics department so we don't have a periodic table, but I brought one. Where are we? Where are they? Titanium, oh, these two are almost identical, which is why I have trouble remembering which way around they are. But it's titanium, zirconium, hafnium, they're all in group 4, they tend to form 4+ ions. It was indeed zirconium, hafnium. And titanium will form the chloride TiCl4, which is a liquid, and therefore does not concern us in this course about 3D solids. Zirconium tetrachloride is a solid because it forms a structure where the formula is that, but the structure is that. So it's just edge bridged octahedra. Why does it do that? Because it's bigger. You can get a higher coordination number. So it polymerizes, and therefore zirconium tetrachloride is solid. You can still sublime it, you can purify it by subliming it, it can go through a molecular phase, but it's a periodic structure. So you could think of it as a polymer of that unit, and the unit polymerizes by forming edge-bridged structures. So there's an example of edge-sharing octahedral. And also niobium does the same thing. The difference is that, so you did second year last year, so you probably didn't do as much on this. I used to teach the second year D-block course and you did a lot more. But comparing zirconium tetrachloride with niobium, which also forms a tetrachloride, the difference is that niobium's got one more electron. Apart from that, it's much the same. But if you've got niobium, here, and that's your repeat unit with another niobium, then if you've got an unpaired electron there which has not been used and an unpaired electron there which has not been used, then you can get some metal-metal bonding. Because I think you probably did last year do some metal-metal bonding in the heavy D block. You know that heavy D block does metal-metal bonding. So because you've got one more electron there because it's niobium in group 5 rather than zirconium in group 6, that's the only thing you're changing. And the structure stays predominantly the same, but given that that's a bond, if that's a bond, then there's nothing for this one to do with the next niobium. And so you'll get a pair which is bonded, and then a pair which isn't, and then a pair which is bonded, etc. So etc. So in fact, the repeat unit is it needs about that much really to describe the whole thing. So there's a structural distortion there, which is due to d-electron effects. And I'm sort of running ahead by myself here because that's what we're going to talk about next time. Tomorrow we'll talk about other distortions from simple packing due to d-electron effects. But there's one example. So that's two examples summarised there: zirconium tetrachloride and niobium tetrachloride, which in which the structures are described by edge sharing of octahedra. Face sharing, not sure what that was supposed to say. They're not terribly important in three-dimensional complexes. There are a few isolated complexes that you have that shape, but there's not that many examples in 3D solids. Now, sharing of tetrahedra, corner sharing, very, very common indeed. Lots and lots of phosphates, borates, etc. Have got that sort of structural unit. So you should be aware of that. Now the edge sharing one is what you get in probably in the molecular case. You look at that as a molecule, and that's diborane, isn't it? E2H6. But in the polymeric case, that's beryllium dichloride. So again, there are simple ionic solids which form these lower coordination shapes. Why does it not form a three-dimensional shape? Because beryllium is too small to get up to 6 coordination to do, well, what we would like to do, probably would like to do that. But beryllium is far too small to do that, so it has nothing to do with 4 coordination. And therefore, you only get one-dimensional polymerization, lots and lots of these edge-sharing complexes. So, if you wanted to think about how that works, that's your repeat unit. It's basically that. I might like to add some brackets to make sense of that as a stoichiometry. That now makes sense. Okay, so you've probably, I think, if you check back in your first year or second year main group notes, have seen that structure in a different context. But in the context of polymeric structures, we should bear in mind that we don't have always just 3 dimensions. You can have 2-dimensional and 1-dimensional periodic structures as well. And those are better thought of in terms of sharing of polyhedra than they are in terms of close-packed lattices with holes filled. Although there is a little bit of overlap in how you can describe things. One thing there is definitely not is there are no examples of phase-sharing tetrahedra. Because if I pull that round to make those contact, then then that will mean that these get even closer. Just pulling these round together, those 2 atoms will get closer, and they're already pretty close when you've got tetrahedral. So tetrahedrals like that, and if it pulls them together to do that, they get too close, and you get core-core repulsion between the 2 metals, and it just doesn't happen. You don't see them. So thinking about how those concepts allow us to try to describe slightly more intricate structures. Another 1-to-2 structure. Fluorite is a 1-to-2 structure where one atom is happy with 4 coordination, but something like titanium dioxide is not going to be happy doing that. The anatase structure of titanium dioxide, we've got 2 mineral forms, there's anatase and there's rutile. The anatase one is based on close packing of cubic close packing of oxides. The rutile one is hexagonal packing of oxides. In both cases, half of the octahedral holes are filled. If we filled all the octahedral holes, it would be a 1-to-1 compound. Fill half the octahedral holes, we get a 1-to-2 compound. 2-to-1 compound. So, trying to see how that relates to a face-centered cubic lattice with half the holes filled is a challenge. I quite understand that. Perhaps the simplest thing to do is imagine the sodium chloride lattice where half of the sodiums aren't there. And that gets you somewhere close. The other point about it is that it's slightly distorted. They're not actually all in a plane anymore, so that's moved up a little bit. So it does get distorted. And that means that we have to use a bigger cell to describe the structure. Because it's no longer, it's a lower symmetry. If we're only filling half the holes, we need to twice as big a cell to describe the whole structure. So approximately, you've got, it's quite a struggle, but I think you can see, if I point that one, that one, that one, that one, and that one, 1, 2, 3, 4, one in the middle, that is your face-centered cubic parent structure. And that's one of the octahedral holes getting filled, but there are other octahedral holes that aren't filled. What do you need to recall? I suppose all you need to recall is that that stoichiometry is explained by having half of the octahedral holes filled. That gives you a 2-to-1 ratio. All comes back to knowing that a face-center cubic lattice has got 4 atoms at each point in each cell, and it's got 4 octahedral holes and 8 tetrahedral holes. So you can describe that as half the octahedral holes, and that describes a 1-to-2 structure. Okay, the other way that you can do that, rutile is one way to fill half the octahedral holes. So it's a distorted CCP oxide array. The cation that thereby gets octahedral coordination, which will quite strongly be preferred for many cations. And the anion only gets trigonal planar. It only gets 3 coordination. 1, 2, 3 into the middle there. And it's an oxide, it doesn't matter too much. And there's probably a fair degree of covalency in that. Right, so looking at that cell, counting these more complex cells, it's all the same really. If it's a face site, it counts a half. If it's a corner site, it counts 1/8. If it's an edge site, it counts a quarter. And you can check it yourself. If you can't work out, come and see me in the office hour and we'll go through it. But that is TI408, and therefore it's TiO2. Now, the other way, oops, yeah, okay, we'll look at the cadmium chloride, which is, I'm not sure what's happened with the animation here. I think there might be an error with the animation. Yeah, cadmium chloride is another 1-to-2 structure. So it's very like rutile, sorry, it's very like anatase. It's just the other half of octahedral holes are filled. Instead of filling one in this layer and then one in this layer like that, you fill all the holes in one layer, and then you leave a gap, and then you fill all the holes in another layer. So if I look at, we might be able to do this on here, we'll see. Does that work? Well, if I put it that way, where's the colour show? Yeah. Put it that way, I can see that there's a green layer there, and there is a grey layer there and there. If I fill those ones and leave those ones empty, then I've got cadmium chloride lattice. So cadmium chloride lattice is also half the octahedral holes filled, but it's all the holes in one layer, and then it's got a layer completely missing. And so that means you've got chlorines packed with chlorines, there's nothing in between holding them together, which is kind of, if this is really Cl minuses, then why would that want to happen? It's a bit difficult to buy that as a concept, but that's what's happening here. Those are the chlorides, and those are the next load of chlorides, and there is nothing holding them together with those apart from induced dipole, van der Waals interactions. Now that fact of itself probably is explained by there being a considerable degree of covalency. So it's not really Cl minus, it's Cl delta minus, because there's covalency in that bond. So if you get something with a layered structure, that of itself is consistent with the idea that you have a significant degree of covalency, reducing the negative charge on here, so that you don't get quite as much electrostatic repulsion between that layer and the next layer. And what the main subject of this lecture is, which I want to get on to soon, is about assessing how much covalency and ionicity is in bonding. But one clue that the ionic model is a gross approximation, and it isn't really terribly applicable, is when you get layered structures, because that tends to imply covalent bonding. So 70% octahedral holes filled, therefore it's 1-to-2 geometry. So it's what you tend to get with more polarizable ions. So it's alternate layer filling, as opposed to half the holes in each layer being filled. So if you do that, the cation gets to be octahedral, the anion gets to be this trigonal pyramidal, sort of a bit like ammonia bent structure. And the connectivity of the octahedra is that they share edges, and you can see the edge sharing octahedra in layers with gaps between the layers. Right, okay. So the final one, which we didn't really talk about much previously, the final way of doing 1-to-1. So far we've got quite a few ways of doing 1-to-1. We can do sodium chloride, all octahedral holes, or we can do anatase, half of the octahedral holes in each layer filled. Or we can do cadmium chloride, which is all the octahedral holes in alternate layer filled. Or we can do cesium chloride, which is different. Cesium chloride is not post-packed. It's not based on cubic onyx and post-packing. It is related to the body-centered cubic. If all of the atoms were the same, then that would be a body-centered cubic cell. But technically speaking, it's wrong to call it BCC because those are cesiums and those are chlorides. Or I could just as easily have selected a cell where chlorides were at the corners and cesium is in the middle. Because what that is two interpenetrating primitive cells of chlorine and of cesium. And that way it's shown there that it's a primitive cell of cesium, one at each corner, that's all, primitive. And there's one chlorine in the body there, but when I put the other cells around that, then that will eventually describe a primitive array of chlorides as well. This is the structure shown with lots of cells put together. And you can see here that we've got chlorides at the corners, but I can actually see that I've got a square defined by the purple ones as well. So there are two interpenetrating primitive cubic arrays, and it's the other one-to-one structure you get, and it is the best one-to-one structure where if that was the same size as that, if the ratio of these two is close to 1, I'll get that structure. Or at least I should get that structure. The problem with that structure is that each thing is 8 coordinate. It's easy to see that the chloride is 8 coordinate. It bonds to each of the corners of the cube. If you look here, you can see that the cesiums are 8 coordinate as well. So it's mutually 8 coordinate, 8, 8. Cesium chloride is 8 coordinate, sodium chloride is 6 coordinate, zinc sulfide is 4 coordinate. So that's phase sharing cubes, cesium chloride. Okay, you can see all of these things in Glorious 3D moving around if you look at Lattice Structures Part 2 on YouTube, or also I recommend ChemTube 3D, particularly because ChemTube 3D has structures on it where you've got one unit cell, and like this, it shows you what it's like with the more unit cells packed around it, you struggle to see the coordination geometry. So you can have a look at them for yourself, until you really get to know, particularly the CCP ones. Now, I said that I would squeeze in, we'll do 5 to 10 minutes on Miller indices again. You've had Miller indices with Dr. Pritchard, but they are relevant to solid state chemistry as well in many ways. So I thought I would just go over them quickly again and emphasise one extra fact about them. Miller indices are planes which pass through the axes ABC of a unit cell at points which are the reciprocal of the H, K and L values. So if you've got a Miller index 100, that means that you are thinking about a plane which goes through a point which is the reciprocal of 1, which is 1, the reciprocal of 0, which is infinity, the reciprocal of 0, which is infinity. So if that plane is going to pass through the B and C axes at infinity, in other words, if it never passes through B and C, then that means that it must be parallel with B and C. So you're thinking about a plane which is it's a plane which is parallel to the BC plane, but which passes through A at one cell along. If you've got, oh, this is where we can do, yeah, here's my cell again. So that face there that you're looking straight on at is a 100 face, and that is a 101 face, and that is an 001 face, and they're all the same because it's a cube. If I chop, what have I got for the next example? Yeah, so all the faces of a cube are all interchangeable, they all look the same, but the unit cell faces are not the real surfaces. And the reason the step further on that I'm taking you is that Miller indices came before we really knew about the insides of crystals. This is if you are working in a diamond shop in Amsterdam, chipping corners off crystals to make pretty diamonds for rings, you know all about Miller indices, because the bits that you chop off are chopping along crystal planes. And if I chop off that atom, then I will get, well, what have I got? I've got a plane which is one way along that way, one way along that way, and one down there. That's 111. So taking a corner off the cell gives us the 111 face, and that 111 face has got a particular arrangement of atoms around it, you can see that it's basically, if you look at a 1-1 face, you're looking at one of the hexagonal layers. When we started talking about this, we talked about building up layers. 1-1-1 is a layer face. And a real crystal might be a perfect cube that's just got 1-1-O's on it, but very frequently it'll have bits locked off and it's got a 1-1-1 face on it. And the surfaces of crystals are very important for reasons not just of being able to make pretty jewels that sparkle, but also because reactions happen at crystal surfaces. So that's 1-1-O. I think we've got some more. Yeah, so there's a picture of all those different faces, the 001, 010, 110, they're all the same basically. 110 means it passes through 1, 1 and passes through Z at infinity, in other words it's parallel to Z. And so Z's down there, that's the 110 face, chopping right the way through the crystal down there, so I need to take all that off as well. Oops. I think that is basically what a 110 face looks like. Actually, I think, is that one out there? No, that one shouldn't be there either. That's all that's left. If you chop down 110, it looks quite different. So 110, two O's halfway through the cell, I think we've seen that one before, and one of the corners off is 111. All of these are different ways that you can chop up a crystal and give you different crystal faces. And the way that a crystal face looks to a reacting molecule is a very important concept. So if we look at the FCC cell, face centered cubic cell, 100 is like that. I'll have to build this again. I think we're happy enough what a face centered cubic cell looks like. I'll just highlight that's just standard face centered cubic cell. Looking at the surface, it's got one at the corners and one in the middle. And you can see that the arrangement of the atoms, looking at that, is pretty much they're all lined up squares, 90 degrees. So the surface coordination number is 8, because we've taken away 4 from the top. The bulk coordination number is 12. The point being, surface is different to bulk. If you're in face-centered or hexagonal cubic, the neutral coordination number of the atoms inside the cell is always going to be 12, the maximum possible. If you have some at the surface, it's going to be lower than that. That makes it more reactive. The surface is different from the bulk. The surface is more reactive than the bulk. But that's just one cell, 100. If we chop it down 110, like we just tried to do with the cell there, then what you end up with is these rows of atoms that we can just about see. If we look here, we've got a row, and then we've got a row further down, and then a row further up. So that's what we're seeing here. So that's what that looks like to a reacting molecule. Now in this case, the surface coordination number is only 7. You can see I've had to strip away quite a lot, and these are relatively low coordinate. 1, 2, 3, 4, 5 I can see there, but the next cell along will give it another 1, another 2. So the surface coordination number is even lower, and that means that it's more reactive to molecules. So 100 is actually very often the face of a crystal that might be most associated with catalytic reactivity. 111, we've just spoken about this chopping the corner off. If you look at 111, then the crystal's left, you are basically looking at your layer of spheres that you initially started with, and that's the repeat unit there. So 111, I'm not sure what that's feel right in the notes, I think. So 110 is the most reactive, and the concept of these Miller indices being related to real crystals by virtue of the fact that their surfaces are made up of any one of these structures is important in catalysis. So for example, we can use STM nowadays, if we're lucky we can get down to coordination, get down to atomic resolution, and we can see this is 100 because we can see that that looks like a 100 surface. They're all lined up with 90-degree angles, all squares. You can see that, yes? So that is 100 surface, and this has got some nitrogen on it. And you can see, for example, that that's still N2, the nitrogens are still bonded, but that's just a nitrogen atom. So you bond strongly bonded molecules to the surface, they start bonding to the surface, and that means that their own bonds weaken, and that's what makes surfaces important in catalysis. It's called heterogeneous catalysis. Critically important. If you're going to study catalysis, you need to know about Miller indices, you need to know that different surfaces have different reactivity. So looking down at nickel 111 here, we can see that's 111 because it's hexagonal packing, just like the diagonal 111. And in this case, we've got some gold atoms stuck on the surface. So just to make the point, those are 90 degree, which is the surface you expect on a 110, sorry, a 100 phase. And those are hexagonally packed, which is what you expect on a 111 phase. You can see that the gold atoms are changing the nickel, that's why they're flowing a little bit more brightly in the STM. So just to make that point, you should be aware of the fact that Miller indices are not just for crystallography, they're also critically important in real things like catalysis. And I don't have any more time to tell you much more about that, unfortunately. But we better get on to what we're supposed to talk about today, which is it ionic, is it covalent? In an ionic crystal, we can think of the ions, obviously they need to be charged to the ions. Very, very primitive models of packing assume that they are like snooker balls, that they're incompressible spheres, but a bit more realistic model considers that the ions have got some squishiness, they have some elasticity, they can be compressed, and they certainly can be polarizable. If they get polarized very strongly, then you move into the situation where you're really talking about significant covalency. But it's a spectrum situation, there's no sharp dividing line, as we shall see. So, the thing which holds together crystal, like a sodium chloride crystal, is the charges, the electrostatic attraction between charges. And the thing about electrostatic bonds, ionic bonds if you like, is that they are not fussed about where the orbitals are pointing, they're not fussed where X and Y and Z is, it's just, and we can describe that as being non-directional, it's just the magnitude of the charges, that's all that counts, so you don't need to bother about orbitals. If it was just down to electrostatics, everything would want to be this cesium chloride structure, because in that structure, each cation gets to be surrounded by 8 anions, and each anion gets to be surrounded by 8 cations, which is, electrostatically, that's going to be what's going to want to happen. But it doesn't always happen. So you're going to maximise the electrostatic attraction by maximising the number of contacts between the central ion and the nearest. So, as I was saying, cesium chloride would be best in theory, but you're limited by the fact that the like ions, the cesiums will repel other cesiums, the chlorides will repel other chlorides. And it's just the balance of those charges that allows us to describe the structure. And finally, we have to bear in mind that you do have to have, if something's going to be an isolable solid, it's got to balance, it's got to be locally neutral. Overall, the charges have to balance. And it almost goes without saying, but sometimes people forget that. These things work best when you're looking at things which most closely fit the model, which are alkaline earth metals, group 1 and group 2 metals, and very electronegative, not very polarizable anions. So oxides and fluorides behave themselves, they follow the rules if we assume the ionic model. Now the problem with the ionic model is that it's useful to think of the size of ions, and the problem with that concept is it's not terribly well defined. Even if you look at a prototype ionic solid, lithium fluoride, you've just been doing the previous unit all about X-ray diffraction. The thing which diffracts the X-rays is the electrons in the atoms. What X-ray diffraction measures is it measures how much the X-rays are getting deflected by bumping into the electrons surrounding the atoms. And it's very, very good at telling you very precisely what the distance between the centres of two atoms is. Incredibly good at that. It's not quite as good unless you're very, very careful about telling you where the surface, where does one end and the other one begin. If you get very good data, very low temperature data, down to close to absolute zero to get this sort of data, then you can describe an electron density map. Finding the core electrons is easy. The core is the middle electrons. But the valency electrons are much more diffuse. You don't always really know where they are. But the best guess we've got here is a lithium fluoride, very low temperature data. And we see that they're pretty much spherical. Certainly the fluoride looks pretty spherical because it's unpolarizable. You can see the lithium's getting cooled around a little bit. It's not quite spherical on the outside. And although you can see that the electron density gets less and less and less, these are the contours, like an ordnance survey map. It gets less and less and less, and then it starts to go up again. Where is the actual cut-off point? That's the big question. And the answer is there are many, many ways to quantify that cut-off point, and they all give slightly different answers. And that's inherent in the fact that you're looking at a minimum which is really quite broad. So if you look at Mulliken, he'd say, right, the cut-off point is there, and therefore that's how big the fluoride is, and that's how big the lithium is. But other ways can describe other ways of chopping up where is the end of one atom and where does the other one begin. It's not easily defined. You can very precisely define the distance between that one and that one. That's not the question. But defining where one atom ends and one ion ends and another one begins is actually a tricky problem with many different answers. Goldschmidt is one, Howling is one, Mulliken is another. Shannon and Pruitt are popular ones, but you just pick one. As long as you pick one and don't mix up with other ones, then you're okay. Right, so ions in general are spherical. The model assumes that they are perfectly spherical. Ions composed of the central core, that's most of the electron density, but the outer sphere doesn't have much electron density, so it's quite hard to know, really. Very accurate interatomic distances, but tricky to get the ionic radii to any degree of precision. Right, and therefore there are lots of different sets, and as long as you're picking one set and don't mix them up, you'll be okay. General point, it's worth remembering, if you get a higher coordination number, even for the same, I can look up an ionic radius for magnesium, and there'll be one number for magnesium when it's in a 4-coordinate environment, and another larger number for when it's in a 6-coordinate environment. So ionic radii are not fixed, they depend on coordination number. Higher coordination numbers get larger radii, because there's more other ions to keep out the way of, more electron-electron repulsion from the ligands, they stay further away. Right, so it's fairly important. I said that everything would be cesium chloride if it could. If the ion sizes are very, very closely comparable, then you get approximately body center cubic packing. But if the ion sizes are very different, then it doesn't work. So if you've got, there must always be contact between the cation and the anion. The anions don't have to be in contact, but you must have contact between these. So it ends up you get a smaller cation and even smaller cation. Now these are starting to, these are now in contact, they can't get any smaller, and now this is so small it's rattling around in the hole. And so in order for that to maintain proper contact with the counter ions, it needs to get smaller, it needs to drop its coordination number. So there's always a critical point after which you can't get the higher coordination number, it has to go to a lower coordination number. Those critical points are calculable by fairly simple Pythagorean geometry, but I'm not going to do that in the lecture. Just going to give you the result of those. The result is, if you've got a ratio of the cation to the anion, which is from 0.2 to 0.4, it's likely that you'll have tetrahedral coordination. Anything between 0.4 and 0.7 will give you 6 coordination, and anything from up to 0.7 to 1 will give you 8 coordination. So the closest matching of sizes gives you 8, next closest gives you 6. If you've got one much smaller than the other, you'll have to stick with tetrahedral. That's the situation you get here, for example. Right, so those are the numbers. And an example there, potassium and iodide. We can look up tabulated values of potassium iodide. You get a radius ratio of 0.6, and that's smack bang in the middle of octahedral. And so on the basis of radius ratios, we expect potassium iodide to have the rock salt structure like its close cousin sodium chloride, and that's spot on, it does. And so we can look at, we can calculate these ratios given tabulated values. These particular ones are Durana and Adrian, but there are many others. I'm giving you these numbers. And so it looks like, for example, lithium fluoride should be body center cubic, but unfortunately it isn't. It's sodium chloride, it's rock salt. It looks like sodium fluoride should be body center cubic. Unfortunately it isn't. So the radius ratio rules don't really work all the time. They work quite often. They work correctly. They predict the sodium chloride structure for all of these, and they predict the sodium chloride structure also for these. But they don't correctly predict in other cases. So those are the ones where it correctly predicts the cesium chloride structure, but it's wrongly predicting cesium chloride for these ones. These are actually sodium chloride. So it gets it wrong slightly less often than it gets it right, but there's not a lot in it. It's slightly better than random guessing, but not much. So many structures don't actually obey the radius ratio rules. And that is because it's an oversimplistic model. It ignores the other bonding contributions. The other bonding contributions can be a slight degree of covalency, particularly the iodides. They can be due to the fact that the ions are actually quite squishy, so the iodides get compressed so as to make them fit. But it's just a qualitative rule of thumb that gets it wrong almost as much as it gets it right. So it's better if we can have other ways of dealing with this, which we'll deal with in the next 10 minutes. They are, firstly, you can measure crystal lattice energies. You can do that in an indirect way, not in a direct way, but in an indirect way. They're always very largely exothermic. Only for a crystalline solid will we have a lattice energy. It can be so large that it can do crazy things like send combustion in reverse. I can burn carbon dioxide and make carbon, which is back to front from normal, if I use it to burn magnesium, for the simple fact that magnesium oxide has an enormously large lattice enthalpy because it's a 2+ ion and a 2- ion, and it's very, very tight. And so that means that delta G is very, very negative for the lattice energy of MgO, and that's what it looks like. I was in the chemistry theatre, I could maybe have squeezed this in and done this for you, but we don't have extraction here. That's MgO, that's a block of dry ice with magnesium burning in it. You get a good amount of light and it produces carbon. A little reprise for Miller indices. Basically, these are massive numbers and there's no way to directly measure U, the lattice enthalpy, but we can indirectly get it. Just to make the point that this is another SEM image of the product of that reaction just on the picture, the reaction of magnesium with carbon dioxide. You can see that you have square crystals because magnesium oxide has got the rock salt lattice, just like that. So you can see in the SEM that that's a square there, and this is a slightly bigger square there. What's more, you can see that there's a chop off there. I think that's a 1-1-0 plane being chopped off there. So you've got almost 45° angle, as you can see all that. So that is magnesium oxide, but it's actually got a carbon coating. So what we've made here is sort of nanocrystals of MgO at 200 nanometers there. So some of these are about less than 100 nanometers. Nanocrystals of MgO coated in carbon, graphene really. Okay, so the way that we quantify these numbers is think about thermochemistry. This is just revision from A level, I think, really. So we'll just get quickly through this. We start with the standard states, and we need to make the sodium gaseous. So we've got solid going to sodium, gas. We've got the bond enthalpy of chlorine going to chlorine atoms, gaseous. So we've then got the ionization energy of sodium to make sodium plus and electron minus. And then we've got the electron attachment enthalpy of chlorine that actually buys us some energy, giving the chlorine the electron. And then what we get most of the energy out is from going from there to there. We can measure all of these, and therefore, and we know what that is, we can measure that, heat of formation, and by difference we can calculate what the lattice enthalpy is. It's a von Haber cycle. Right. So if we know what the distances are, there's another way to calculate. So that, if you like, is an indirect, but it is an experimental measurement. A von Haber cycle is an experimental measurement of lattice enthalpy. But if we've got a decent model that just depends on electrostatics, we should be able to calculate it as well. So there are majorly two forces. We've got the simple electrostatics. Some of you might remember this if you've done physics, or perhaps even some first year notes. I think we've got as far as this. 4 pi epsilon naught. 4 pi is a number. 4 times 3.14 something. Epsilon naught is the permittivity of free space. It's how much can the electrostatic charges see each other through a vacuum, permittivity of a vacuum. R is the distance separating the charges. Z plus and Z minus are the magnitude of the charges, whether it's 2 plus or 1 plus, etc. Z equals 1 for 1 plus, Z equals 2 for 2 plus. And E is the charge on an electron. So if you multiply that by that, you've actually got to measure how many coulombs, how much charge you've got. Okay, so that's Coulomb's law for one ion attracting another ion separated at that distance, which is fine if we were dealing with a sodium chloride molecule, but we have a sodium chloride lattice. So what we have to do is assess the attraction of that ion for this one, but also for that one, that one, that one, that one, and that one, because each sodium is surrounded by 6 chlorides. And that, there's our sodium, there's our 6 chlorides. That's where this comes from. And the R is because they are separated from the chlorides by the interatomic distance, 1 sodium, 1 chloride. The next term, the negative term, and it's got 12 R root 2, and that's because the next ions along are the, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Next opposite away sodium. They're going to repel, so that's why the sign's opposite there. 12 because there's 12 of them. R upon root 2 because if that's R and that's R, the distance there is root 2R. Pythagoras' theorem. Yes? So, and then the next furthest away thing, it's actually we're back to attractive terms now. And we've got rather further away chlorides from that first sodium. How much further away? It's actually root 4 that distance. No, it's not. It's our root 3. There's 8 of them, 1 at each corner, and it's root 3. The body diagonal is root 3. So there's root 2 along there, 1 along there, so it's root 3 along there. And there's 8 of them, etc., etc. But they do get smaller as you go further forward. But this particular set of constants, which is all a big multiplier for the same thing, that's 1 plus, that's 1 minus, that's the electronic charge, that's all the numbers. Just depends on what these numbers are and what R is. Small r gives you big numbers because R's on the bottom. That's the important thing. The important thing to remember from this is R is on the bottom, so small ions pack strongly. Small number there means big number there. And big numbers here, large charges, give you large ionization energies. We scale directly. Now, you can take all of these, showing you where these come from, and this, you can generate this basically just from thinking about the packing using Pythagoras. You can collect all these together, and that number will be the same irrespective of what R is. So that number, that multiplier, depends just on the lattice. There's a particular number for the sodium chloride lattice, the rock salt lattice, and that number is known as the Magdalene constant. So if you take all the actual arithmetic out, just put the R in this bit, then we can just sum that up, and we can record that value, and it will be a particular value for the sodium chloride, and it will be a different value for calcium fluoride, etc. It depends on the lattice type. And we've got to remember that if we're going to do kilojoules per mole, we've got to have Avogadro's number, and that gives us an equation that allows us to calculate in kilojoules per mole what what a lattice enthalpy is. So the Magdalene constant will depend a lot on what the first coordination is, because the biggest term is the first one, and for 6 ions you get a 6 there, but it will be a bigger number for other things. Here it is for cesium chloride 1.7, well 1.76, sodium chloride 1.75, zinc sulfide 4 coordinates, only 1.6. Calcium fluoride, because there's 2 ions, it's 2.5. Titanium dioxide is 2.5. So there was a guy called Kapuscinski who was just a bit lazier at maths, I guess. He realised that those numbers are both pretty similar, and they relate to things that have got 3 ions in them. So if they've got 3 ions in them, you've got about 2.5. And if it's got 2 ions, then well, they're all roughly about 1.7-ish. So there is one number depending simply on the number of ions, and that was what Kapuscinski contributed. But before we do that, if we just thought about electrostatics, then everything would just sit together into singularity. It would all just suck into itself. The reason that we have particular equilibrium geometries is because we also have repulsion. So far we've just done this, and the closer the ions get, the more stable it gets, the lower energy it gets. So that's the attraction bit. That can be described by what we just did. But there's also a repulsion bit, which is when they start to bump into each other, and you get core repulsion between the pairs of the core electrons in each, then it just goes massively up. And that can be described with this, which I'm not going to spend any time at all, and really just notice that what that term does is it's putting a repulsive term in. So the additive, you get the typical potential well like that, and the optimum distance in the crystal will be at the bottom of that well. That's what the equilibrium distance is. Right. So that equation, which includes both the attractive term and the repulsive term, is known as the Born-Landy equation, same Born as Born-Haber. So we can do experimental measurements and compare them to calculations. And then, as I was saying earlier, Kapuscinski noticed that A was almost the same for things where ions have the same number of units. So it's about 2.5 or 3 when you've got 3 ions. And so here an even more simplified version, which has just got a number, Z plus Z minus, and the distance between the ions in it. Okay. And I guess we're going to have to stop there. I'll still not, I'll definitely catch up next time.